Hello everyone, and welcome to part 2 of our look at BitRAT. In the last video, we deobbed the stage1.net executable, and then we decrypted the second stage that was included as a resource. Then we used UPX to unpack it. So now let's look at two specific items of note. The first item we need to look at is the anti-debug features that this uses. So it's using a different version of anti-debug that I don't normally see at these two locations. It's being resolved at runtime, so you can't see the import in P Studio, so you don't know to plan for it. And the technique it's using is NT-DLL, NT set information thread. Basically, a thread is hidden from the debugger, and then after the thread is hidden, it'll continue to run, but the debugger won't receive events related to this thread. So this new thread can perform anti-debug checks, or basically anything else it wants. So here's another weird part of it is, if you set a breakpoint in the hidden thread, or if the main thread is hidden from the debugger, it'll basically crash the process and the debugger will be stuck. So how do you spot it? How do you get around it? So if you're stepping through code in x64 or 32 debug, and you end up seeing new threads spawn with event communication between them, and then all of a sudden you see the malware running without any changes in the debugger, then you know that this is happening. So the way you can get around this is by using specific options in the Silahide plugin. So let's take a look at the way that it actually loads this anti-debug tool at runtime, and then let's look at the options in the Silahide. So let's take our first location here, and let's go over to Ghidra, and let's go to this location. So you can see there is a loop at this spot here, and then there's another loop down here. Let's set a breakpoint on this first loop, and let's go over to our debugger and see what it looks like. As for Silahide options, let's go to plugins, Silahide options, and the one we want is the set information thread, this first one right here, but you can check these others if you want as well. So if we set a breakpoint on that location and we restart this, so there's our entry breakpoint, and it should be the next one we hit. Yeah, A64. So here's the next one that we hit. So let's go through this loop and let's see what it's doing. So here's our jump. It's going to move in something to EAX. Let's go see what that is. So it's going to move in items from this memory location into EAX, and then it's going to perform some decoding on those. So just like we saw over here, there's a loop, very basic loop. We'll just step through this, and let's see where it's actually putting them in. So right before the end of the loop, it's putting what's in DL, which is the lower part of the register for EDX, into ECX plus ESI. ECX is incremented, as you can see, so it will increment and move this memory location in each iteration of this. So let's follow this in the dump. There's nothing there right now, but it's going to put in the character in this location. So you can see that that's there now. It's going to increment ECX, and we're going to go through it again. It's comparing ECX, which is our loop counter here, to 16, and right now it's 1. So let's go through this a few more times just so you can see. Now it's going to move the character T into this memory location. It should be the next one right here, and there you go. So let's go ahead and we'll set a breakpoint right after this on this XOR. And let's run to that. We have to remove this breakpoint first though. All right, so let's run to that right after this loop. So right after this loop, you can see that we decoded NT set information thread. And now let's take a look at this second loop right here. It is at AB3. AB3 is right here. Let's set a breakpoint on that. We're going to run to that. So in this loop, let's get to the end of it here. Now we're moving the lower part of the register from EDX, which is DL, into this location right here. So let's see what's in this location. And it moved an N to this location. So let's jump to right after this, set a breakpoint there, remove our previous breakpoint, there we go. And let's go ahead and run to that. NT DLL.DLL. So by using some very basic decoding and two different for loops, it went ahead and decoded the NT set information thread. It decoded the NT DLL.DLL, and then it's going to go ahead and load those. And that's why you don't see it. So now that we've got our options set in Silahide, we can get around this and we can go ahead and set breakpoints further in on functions or specific memory addresses, and we don't have to deal with that. So for the second thing we want to look at, there's something unique about this sample in that it uses Camellia to decrypt its configuration. So that's symmetric encryption, and it's similar to AES. This one uses 128-bit CBC. So the entire decryption process takes place starting at 50D F4B, and it first creates a key out of multiple portions, and then it takes that key and performs the decryption I mentioned. So the most unique or interesting thing about the sample is the way that it generates the key. So that's what we're going to look at here. Let's go to where this is. So here's the start of the key creation function. If you scroll down just a little bit, the first part that we are really interested in is right here. It's moving in some stored values, and then it's going to loop over those. So what's stored at this location? Well, you can see it's over here. Ghidra already shows us. It's OX55, 3D, 34, 36, 4E, 6D, and those are both stored at these locations here. So the loop here is just a simple decoding loop. And let's see what that looks like over here in the debugger. So we're at the same starting spot here. Let's get down to where this loop starts. And the loop starts at 50E77. So let's go there. So at the beginning of this loop, it moves something into EAX. There's our 55 that we saw that it's moving in. And then it subtracts 8, multiplies it by 25, and then it does a couple of division operations on it. And it moves the result from DL into this new location here. So it moves the lower portion of the register into this new section. So let's see what that is. The first one is 37, or the number 7. So instead of stepping through this the entire way, let's just set a breakpoint after the jump, and we'll run to that. So our result from this first decoding loop is 78H, F326, F87. Okay, so now let's go down a little bit further. So now we have something interesting here that's being moved into EDX. If we follow it in the dump and then go to this memory location, we can see that it's 437, 455, etc. So there's a hard-coded string being stored here. So now we have our result in EAX from our previous decoding and our string being stored here. So if you jump over this call right here, you can see that EAX is the result, and it takes that hard-coded string, and then you can see that it appends our decoded value on the end of this static string. So let's take a look at the slide here. So like we saw, it moves in static values and performs a decoding loop, and then it appends it. So the next thing we're going to do is it's going to take that, so it's going to take this value and it's going to perform a CRC32, and then at the very end it's going to add an 8. So if we take this value and we want to follow along and confirm that this really is a CRC32, we can put it over here in CyberChef, and we can see that the result is BAF DF77F. So it's BAF DF77F. So what do you get if you add 8 to that? So the result should be BAF DF787. So let's jump until after this and confirm that's the result. So EAX holds our result, BAFD7787. And that's what we had. Okay, so now that we've done the CRC32, so looking at our slide, we've calculated a checksum of this new string and added 8 to it. Now it computes an MD5 hash of this checksum. So let's go down to there. Here's our hash function here. Let's run to that. And let's jump over the hash function. And so now the result is 444194. So if we want to MD5 of this, we have to remember to make it lowercase. So we do that. And then it's a 44194, just like we see over here. The next thing it's going to do is going to split that hash into the first 16 characters. So it's going to split it in two. Let's see that. If we just step down through here a little bit, we'll see that happen. And you can see after this function right here, now EAX only has the first 16 of that hash. So now these 16 characters are going to be the decryption key for Camellia. So what would this look like if you wrote a decryptor for it? So I wrote a quick one in Python, and we can step through the same things that we just saw. So a couple of the things is the magic value that's appended to the static string. That value has been the same across a few samples. However, if it does change, there's a prompt where you can input the new starting hex values and it'll compute the new magic value for you. And that's just like what we saw. There's just some very simple decoding going on right there with the -8, multiply 25, and then some division operations. So then it does strings on the file. We're trying to find the first part of the hard-coded value that goes along with the magic key value. We're also trying to find the encrypted data. Those are fairly easy to regex for in both of these. So now what we're going to do is we're going to take those values and we're going to perform the same decryption items that we just saw. So let's look at that. So the first part is it takes the magic value that's computed with the decoding. It's going to add that to the static value and it's going to make our main starting string value. We're going to do the CRC32 right here on that value. We're going to MD5 hash it here. We're going to split it here. And then we're going to go ahead and do some basic formatting to convert it to bytes. And then we're going to go ahead and run Camellia. We're going to give it the key and it's going to run in CBC mode. The thing that's been the same across all these are the IV is all zeros. So here we're passing in all zeros. And then we're going to go ahead and run the decryptor on it and we'll get our result. The only thing about this code would be that sometimes the starting value for the key is only 16 characters. So it's possible that you could have multiple values that could fit this description and not actually be the portion of the key that we need. So what happens is we can go ahead and try to brute force that. So we take all of those, we put them in a loop, and we just go over it one by one and we just try it. And we'll see which one actually gives us something that we can decode. So if we run this, we don't want to change our value. So now let's give it our file name. And without looking at the bottom part first, you can see that there are a few strings that it might try to use. But when it finally found one that works, you can see that it's using the encrypted data. Here's our encrypted data that we found. Here's our checksum, the BAFD-F787 that we saw earlier. Here's the same hash we saw, and then it splits it, and here's our key. And then here's your config. It's going to reach out to duckdns.org on port 2005. If we want to match up the encrypted value that's being passed in, even before the actual call, but you can see the actual call that eventually ends up to the Camellia decryptor is down here. And right before it calls this, and one of the values it has, if we look at all these, is the first thing being passed in to this function is B122E21E. And you can see that in a couple of these other places over here. But this is going to be your encrypted data that we're going to decrypt. So that pretty much does it for the decryption of the config for this. I'll go ahead and add a link for the decryptor I showed you in the description of this video. And I'm not sure what we're going to look at next time, but we'll see.